That big red tank is the liquid fuel tank, right? And it hit that liquid fuel tank and just blew it to smithereens. And the reason that these things are joined like that is that they have to fit on railroad cars because they're made in Utah and shipped to Florida, right? And there's tunnels on the way, so they can't be too long, right? You know? There we go. Blah blah blah. I think I already said this, didn't I say that? I said that, right? Danger, Will Robinson, right? Okay. Here is this is the full diagram. So this you get from Estes Rocket Company, and these are, we've already looked at like the thrust curves for D12 engines. I'm not sure why they peak like that at the beginning. I suspect that there's no exhaust gases in there. There's no carbon dioxide and water to begin with. So it's like basically an explosion at first, right? So maximum pressure and then it levels out. As a child, I tried to make my own rocket engine. Don't do this, right? But I took a steel pipe and filled it with something that I thought would burn gradually. Didn't burn as gradually as I thought. It burst the pipe, shall we say? Yeah, well, oh my God. You know, this is, by the way, a federal crime to make one of these. This is called a pipe bomb. Okay. I was smart enough not to be close to it when it went off. Right? I mean, I was like, it might burst, so I'm going to be far, far away because if it does, maybe chunks of pipe are going to fly. And so. But it was just tremendous, and I was like, ooh, failure. Okay. The first thing I did as a teacher, a new teacher at a high school, was I bought the biggest engine you can buy. Look at the area under that curve. Yeah? We figured out last time that that's 20 Newton seconds. Yeah? And I hooked that to a lightweight dynamic cart. We had these little carts, and they were beautiful. They had ball-bearing wheels. At least this one did originally. It had nothing left after this. Okay, but it was, and I think they were about half a kilo. Okay, and I strapped the rocket engine on there, right? Okay, and attached the wires to it and set it off. And we went off into the hallway. Should have done it maybe outside. I don't know. But I went outside. I went out in the hallway right outside the science wing at Breck School. And, yeah, there it was, right? Well, you guys can do the math, right? We've already figured out that force times time, right? Force times time is 20 Newton seconds, yes? We did that. It was elaborate. Area under the graph. We drew rectangles. Do you remember this? Okay. Well, let's do a little calculation. If it's a half a kilo, if it weighs about a pound, right? What's our change in velocity? 40. Is that about 90 miles an hour? Yes, it is. Yes, it is. Right? So there we are in the hall, I'm an idiot. I can't divide, I don't know, right? Okay. I light the thing off. I had the students all stand. There was like a raised edge. Like there were windows all along one side, and the students were all standing with their feet off the ground. Thank heavens, As far as we could tell, nobody really saw this because the air instantly filled with this impenetrable sulfurous cloud, which sent all the kids with asthma, choking, coughing into the courtyard, right? As far as we could tell by the scorched marks on the floor, it left the ground about halfway down the hall, right, and started flying at about waist level through the air, right, and it slammed into a brick wall at the end, okay, which happened to be the wall between the hallway and the girls' locker room. Okay, and the kids say that the rumor was that Murray put a hole in the wall. It was a cinder block, and it hit the cinder blocks are hollow and largely fairly fragile. I mean, if you ever haul them around, you're going to break one or two, right? And it hit one of them where there was actually an air cavity inside of it, and it made one of those little like BB hits window holes where it's small on this side but big on the other side, kind of a thing. Yeah, I don't know. They had to. Somebody who probably got paid a lot more than me. Had to go in there and chip that block out and put a new block in. And then, I don't know. And then the kids started writing Murray's block on there. It was a little bit embarrassing. What? I had a discussion. So, they really learned them something that day. I learned them. Look out, baby. There you go. That's the whole story there. Okay, and then this is the diagram from Microsoft Encarta. I think it's like the 1995 version of this, right? But you've got a fuel tank On the space shuttle, the fuel is hydrogen, the oxidizer is oxygen. On the Saturn V rocket, it was kerosene, I think, and oxygen, but I could be wrong. But basically anything that burns with air is going to explode with oxygen, so that's the notion here. And then there are pumps. These pumps are clever. They know stoichiometry, so they know exactly how much oxygen, oxidizer to pump, and fuel to pump so that it combines totally, right? And then I think there's some way of igniting it, some other source, like I don't think some NASA person has to walk up there with a blowtorch and light these, right? And the Saturn V rocket, by the way, lit at 8.6 seconds, right? So 10, 9, 8, 7, between 8 and 7, right? Or between 9 and 8, the thing ignited. Liftoff was at 0 seconds, and even then it was held down, had these clamps to hold it down for some period of time until they could confirm that it was going to go up, yeah? And then once it let go, there was this friction device that it had to like slide a thing through a channel because it was what you wanted to do. You didn't want it to lift off unless it really was going to go up, because there was no convenient way for them to settle back down on the launch pad if the engines failed, right? So you had to be sure that the thing, sure that it was going to go up. But there it is, right? This thing. In Encarta, they explain jet thrust or rocket thrust in an interesting way. I thought this was interesting. If you recall, in a fluid, pressure pushes in all directions, correct? Yes. Okay, so the explosion in here presses equally on the side of the chamber, on the left side, but also on the right side. Those forces cancel out, correct? And it presses on the back of it and the front of the chamber as well, and those forces cancel out. In fact, all the sideways forces cancel out. But there's an upward force on the chamber that's not canceled out because there's nothing down there. That's interesting, isn't it? Right? So if it's 1,000 pounds per square inch, right, and that's 5 square inches of area, well, what did I say, 1,000? Then it's 5,000 pounds of force that's unchecked, right? That's an interesting way to talk about it. I never talked about that, right? Here's I believe they're launching the Voyager spacecraft, back in the 70s. That's what that one is. So that's not, I don't think that's a Saturn V rocket. It's a smaller one, right? So 2 questions. Question 1. What is the steam coming off of the sides of this rocket? Yeah, it's water, condensed water, because this is Florida. It's very humid. Assume 100% humidity, yeah? Okay. So why is water condensing? Why do chunks of ice fall off these rockets? Yes, sir?
Well, I know does it have anything to do with the water, they spray water on the engines?
Spray water. Oh, yeah. Not as much. Hydrogen and oxygen make water. Okay, this is liquid hydrogen, liquid oxygen. Oxygen is a gas until what temperature?
Really cold.
Really cold. These are cryogenic liquids, right? So that's why liquid fuel rockets are a pain, right? Because you've got to put these cryogenic gases, they've got to be really, really cold, right? I think, it's like liquid nitrogen or colder than liquid nitrogen. Some of those, certainly liquid hydrogen is colder than liquid nitrogen, right? So these things are full of cryogenic gases, yes? That means cold, very cold, yes? So the thing that killed the Columbia shuttle was that a chunk of ice fell off of that big fuel tank, right? Was it a chunk of ice? Or was it insulation?
I thought it was like falling over.
Yeah, it was insulation, hit the heat shielding tiles, right? But the insulation, I believe, comes loose or is necessary because of those cryogenic gases, right? Which is sort of interesting, right? So that's one question. Why are they steaming? Why is there ice on the side of it? Because it's full of stuff colder than liquid nitrogen. Liquid nitrogen, you dip a rose in it, drop it on the floor, it shatters, right? We'll try to do this at the extravaganza this June at Tigard High School. The second question, and I always had this question as a child, right? Isn't a 363-foot tall rocket kind of tippy? What keeps it from falling over, especially if you're trying to push it up from the bottom? Do you ever wonder that? Does it slide? See, our Estes rockets, the little model ones, right, fly up a little rod, don't they? Okay, and the reason they fly up the rod is that by the time they get to the end of the rod, they're going so fast that the fins make them fly straight. If you glued them on straight, yes? Right? You're supposed to test the rocket before you fly it, fly it around you and see if it doesn't fly straight, if it does this, that's bad, right? Most of us don't do that. We're just we launch the rocket anyway and it goes, what was that, right? Or did any of you ever try to launch just a rocket engine? We did that. We glued a launch tube onto just a rocket engine. Boy, that's really going to go. Oh my God. never do this, right? The rocket engine flew around. It got to about head level and then flew around. And we think it stayed within a space about as big as this room, just flying around like a big angry wasp, going, right? You know, I think one